So in our last discussion, we defined selection. We looked at what are the necessary conditions for selection to operate, and then we requested you to go and look at 2 videos. I hope you have done that. And then we said that in the next discussion, which is this one, we are going to look at the dynamics of selection. We are going to look at how selection leads to changes in alleles and allele frequencies and genotypic frequencies. Now, before we go there, we need to define one term which actually I have kind of not really used till now, but going forward we are going to require that term, and that is a term I am sure all of you have heard, which is fitness. Okay. Now, what exactly is fitness in an evolutionary sense? And the problem with fitness is that there are many ways of looking at fitness, and just like the concept of species, different people have defined it differently, they have used it differently, and philosophers have written books and books and papers on it. So, it's a slight bit of a mess. Basically, different people have different views about what it is or what it should be. So, those who are interested in the philosophy of what is fitness and what are the various different definitions and how they relate to each other, etc., here is a very nice resource for looking at it. Of course, this is not a part of this course, it is only for those people who are interested in the philosophy of the subject. So, in the context of this course, we are going to define fitness as a measure of the success of an individual to survive or reproduce. Okay, that is about it. So, if for example, some individuals have 80% survivorship and others have say 40% survivorship, then the ones who have 80% survivorship will be said to have a greater fitness. Similarly, if some individuals produce 20 babies and some other individuals produce 40 babies, then the one who is producing 40 babies will be said to have a greater fitness. Now, this particular definition that I am talking about, this actually aligns with most textbooks, for example, Fukuyama and Kirkpatrick, which we are following to some extent in this course. However, I must caution you that we ourselves, I mean me and some of my colleagues, we have actually argued that there are some issues with the above definition, and we have suggested a very different definition to be a better definition of fitness in the context of evolutionary biology. If you are interested in looking at our arguments, this is the particular reference. It is available on Evo Archive, so it is free for you to look at. Now, you might well ask me over here that if you yourself are not very sure about this definition, then why are you giving it to us? The reason I am giving it to you in the context of this course is because in a course we have to look at a lot of standard material, a lot of notions and a lot of concepts which the field generally adheres to, and it will be easier for us to know about those concepts, etc., if we adhere to this particular definition of fitness. However, if you go deeper into the subject, for example, if you end up taking a more advanced course in evolution, then you will figure out what are the issues with this particular definition. But as I said, that is an advanced thing. So, for this course, this is what we are going to think about in the context of fitness as a measure of success of an individual to survive or to reproduce. Okay. So, with that definition out of our way, remember this figure, right? This is how we derived the Hardy-Weinberg principle, and I explicitly said that the good thing about thinking about Hardy-Weinberg in this context is that you explicitly figure out which are the stages where the different assumptions are coming in, and therefore, when you study evolution, you study it in the framework of violation of those assumptions, right. So, if you remember, in this entire framework, selection comes basically in 3 places. The first place is where right over here at the top, where we assume that all individuals have equal fertility. Now, if that condition is violated, you have a kind of selection which is known as fertility selection, but that is not what we are dealing over here. We are dealing with this scenario over here, where you are going from genotypic frequencies amongst the zygotes that have been produced to the genotypic frequencies among the progenies who are going to produce the generation after that, right. So, in this context, remember we said that, as long as the viability of all the genotypes are equal, in other words, there is no selection in terms of viability both at this step as well as this step, then we are going to get what is known as you are going to get no selection if the viabilities are equal. So, obviously, what we are going to see is what happens if the viability or the survivorship of the various genotypes is not the same. So, how will we do that? So, in this particular discussion, we are going to do this using numerical simulations using Excel, and we are going to do a one locus two allele model, which is the simplest kind of model in this context, and doing so we are going to derive some interesting insights. So, what I will do is I will actually show you step by step how to make this Excel file for yourself, so that you know that there is no magic anywhere or there is nothing being shoved under the carpet anywhere. It will take a little bit of time, but that is okay. If you follow me through the entire thing, and if you actually make the Excel file as you see me making the Excel file over here, stopping and making it and stopping and making it and so on, then by the time we are done with this discussion, you will have the Excel file with you, using which you can verify every single stuff that I am going to show you and a lot more, right. And once you do that, then we are going to you are going to be able to explore this entire thing on your own, which, trust me, is a great thing. So, it is going to be a little boring if you just see me doing the Excel. So, I strongly urge that you also do the Excel thing on your own at the same time. If you do not have access to Excel, OpenOffice, LibreOffice or any other office suite will have some kind of a spreadsheet program. I am using very, very simple functions. So, all those functions will be available in those spreadsheet programs. So, you can use whatever you have. So, let us go to an Excel. So, this is just a simple Excel file. So, what we will do is we will do it in a slightly complicated way, but the reason we will do it in that complicated way is that then looking at the simulations become very easy. So, the first sheet we are going to call it param graphs. It does not matter, you can call it anything. And the second sheet I am going to call it simulations. Okay. So, now let us assume that we are doing a one locus two allele model, which means that let us assume that our allele A1, let me increase the, let me increase this a bit. So, let us assume that our allele A1 has a frequency of P. So, this is allele frequency, and therefore, allele A2 will have a frequency of 1 minus P. So, on this one we put allele A1 as P. So, let us go over here. So, frequency of A1, let me increase this size a bit over here, and equal to, we take it from here. So, let us assume, let us assume that we will start with P equal to 0.1, let us say, okay. And we will mark this with yellow so that we know that this is where we have to make our changes. So, here frequency of A1 equal to this value over here, okay. Therefore, frequency of A2 is equal to 1 minus p. So, this is 1 minus p. Great. So, now remember we are saying that this is the frequency in the parental generation. So, now these parents are going to produce the offspring, and these offspring genotypes, they are going to be in the frequency p square 2pq q square. So, we will call p, capital P equal to p square and capital Q equal to 2pq and capital R is equal to q square, right. So, let us make this equal to p into p, this is p square, capital Q equal to 2 into p into q, okay, and let us say this is equal to q square, equal to q into q, okay. So, till this point the Hardy-Weinberg frequencies are being obeyed, because we are going to have viability selection after this, okay. So, let us go back to this paragraph sheet, and now let us have our genotypic frequencies. So, what are our genotypes? Our genotypes are A1, 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 A2 and A2, A2, right. So, these are our genotypes. Now, let us assume that all these genotypes have some kind of a survivorship. So, let us assume this is what we are going to call the fitness, okay. So, the fitness is, these are given as W11. So, A1 fitness is W11, fitness of this is W12 and fitness of A2 is W22, okay. And let us give them some values. So, let us say, just to begin with, let us say this value is 0.9 and let us say this value is 0.7 and let us say this value is 0.3, some arbitrary values. Again, what we will do is we will mark this as yellow, meaning that these are the places where we can make the changes, okay. So, now we are back to our simulation thing. So, these are the frequencies before selection, okay, frequencies before selection, these three. Now, the genotypes have been formed, selection has operated, and therefore, they have survived differentially. So, in other words, now that the selection has happened, what will be their frequencies after selection? Their frequencies after selection. Frequencies after selection is going to be p square into W11, 2pq into W12, because that is the fraction that is surviving to the next generation, surviving to the next stage. So, this is going to be p square into W11, okay, frequencies after selection for A1, okay, I will just call them PQR, PQR, okay. So, this is equal to p square, which means this into this W11 over here, right. Now, here we have to do one extra thing. What is it? So, here when we have this cell E6 being selected, we need to put a dollar sign. So, two dollar signs, one before E and the one before 6. So, $E, $6. Why do we do this? So, when you do this, that means when you are going to drag these when you are going to use this relationship for other cells, from this place it will only pick this value and it will not pick any other values in relationship. In other words, basically we are using it as a constant, that is why. Okay. So, this is p square w11 equal to 2pq into w12. What is my w12? My w12 is this, and again I need to put a dollar here and I need to put a dollar here. Okay, and this is what? This is q square w22 equal to q square into w22, which is this value, and I need to again put a dollar at here and a dollar over here. All right. Okay. So, frequencies before selection and these are frequencies after selection. Awesome. But now I have a problem. What is my problem? If I take the frequencies before selection, if I sum them, okay, what am I going to get? I am going to get 1. Great. That is how it should be. But now that these numbers, this p square, 2pq, q squares have been multiplied by different fractions which are not summing to 1 or anything, therefore, will this sum to 1? Let us quickly check. No, it will not sum to 1. It is not even expected to sum to 1, right? Now, obviously, if you are trying to figure out the actual proportions, then you need to make this sum to 1, right? You need to scale it in such a way such that all these frequencies sum to 1. How will you do this? The simplest way to do this is to divide every single term by the sum of this. So, we will look at the sum of this and we will call it W bar. Why we are calling it W bar, that is something that we will postpone to the next discussion. But as of this moment, let us call this W bar, and this W bar is simply the sum of these three things, these three frequencies. Okay, great. So, now if our thing is correct, if our understanding is correct, then if we are going to divide these, each one of these by this sum, then it should sum to 1. So, let us do that. Equal to this divided by this, great, equal to this divided by this, great, equal to R divided by W bar this. And if what we were thinking is correct, then this should sum to 1, and it does, which is not surprising. Okay. So, what have we done over here? We have simply scaled them by the average, by the sum of the frequencies, scaled frequencies, and these scaled frequencies are now summing to 1. Great. So, these are the actual genotypic frequencies post selection in the offspring generation. Now, from this we need to go to the allele frequency in the offspring generation, right. So, remember, this is frequency of A1, A2 in the parental generation. Now, we have to go in the offspring generation, and for that what will we do? We will simply do p plus half q. So, equal to p plus 0.5 into q, right, and this should be equal to, actually I can just drag this, right. So, what we have done is we have started from parental generation allele frequency and we have gone all the way to the next generation's allele frequency, right. And the only thing that is missing over here is generation So let's assume that this is my generation 0, the parental generation. This is generation 1, and let's say, okay, we'll do that in a moment. So now all we have to do is to drag this for the next generation, and we have the next set of values, right? So this is the same thing for the next set, and now all we have to do is to take this thing, select this entire stuff, and just drag this. Let's see how long we want to go. We have gone up to 160 generations. Let's say we would like to go another 40, so we make it 200 generations. There's nothing magic about 200, it's just a round number, that's all. Okay, that's it. Our simulation is done, right? But these are just the numbers, but it's good to get some graphs out of these things. So those graphs we are now going to draw at this end. We are going to see how P changes over time, the allele frequency of allele A1. So what we'll do is we'll go over here and we'll go to insert, and we will go over here. We are going to place this, and this is the kind of graph, dot with lines is what we are going to select. So it gives you a blank chart, and what we'll go do is we'll go to, we are already on chart design, so we'll go to select data, and now it allows us to select the chart data range. So we'll go to the simulations page, simulations worksheet, and we will select this entire column called frequency of A1, and that's it. We have our graph. So this is what it looks like, and we'll put the legends, although there is only one legend, but still it's actually, yeah, we don't need it. There is just one point, one variable over here. So but we need the axis titles, right? So what is this? On the y-axis we have frequency of A1 allele. So we will select this, and we will increase the font size a bit. Similarly, on x-axis we have generations. So we will select this entire thing, and we'll go to home, and we will increase the font size. Let's see, this is good enough, or maybe a little less. Yeah, this is good enough. Okay, and yeah, this frequency on this side, this should only go from 0 to 1. So we will cut this at 1.0. So that is done, and yeah, we can maybe make it look slightly better, but overall what we want to do, that is coming out of this graph. We can see the we can see the patterns. So that is our first graph, and the second graph that we would like to draw, where do we draw this? Maybe right next to it. The second graph will be the frequency of the genotypes. Okay, so we again do the same thing. What we do is we go to insert, and we again go over here. We select the one which says insert line or area chart, and then we select this particular one, and again it comes out here. And what we do is we go here and we say select data, and in the data thing we go back to our simulations page, and we are interested in knowing the scaled frequencies. So we just select the entire, for 200 generations we select the entire stuff. PQR is fine, horizontal category is 1 2 3 4, so this is fine. There you have the graph. Okay, so this is the genotypic frequencies over time, and yeah, we need the legends over here, so we go to this plus sign, and we need the axis titles, and here we definitely need the legends. Okay, again the y-axis cannot go beyond 1, so we'll make it 1.0, and what else can we do? Yeah, the axis titles need to be given. So this is generations, and this is genotypic frequencies. Okay, again we press Ctrl A and we go to home, and we slightly increase the size, 14. Yeah, good enough. Okay, so what we do now is we slightly reduce the size of the graph. Yeah, okay, so this I think is good enough for us to visualize. Or maybe what we can do is we can bring one of them here, and we can bring the other over here, so that we can visualize both of them in the same view. Okay, excellent. So now what will happen is we can play with the initial allele frequencies, or we can play with the genotypic fitnesses right from here without even looking at what is happening to the numbers over here. I mean, of course we can go back and look if we want to, but we don't really need to do that. So these two graphs are going to tell us a lot of things. So let's start playing with them. Okay, now even before we start doing so, note that in this particular case A1 had the highest fitness, A1 A2 had the second highest fitness, A2 A2 had the lowest fitness, and therefore even though A1 started with a low value of 0.1, very fast it actually climbs to a value of about 1, which basically means the other one goes to close to 0. Now remember, in the previous context when we were looking at mutation, going from 0.001 to 0.1 took depending on what kind of mutation rates we were doing, took hundreds to thousands of generations. So let's see over here what happens if we want to go from 0.001 to 0.1. And okay, so here we have to look at the numbers. We have started with 0.001, and from 0.001 to 0.1, if you can see, it takes just 6 generations. Okay, now of course the precise number of generations that it will take will depend on the values of those things, but you can see that for some reasonably realistic values it's actually very fast. And this is what I mean by saying that selection is a strong force. It causes changes very fast. Okay, so now here you can see that there is a lot of difference between these things, okay, between the three genotypic fitnesses, the survivorship values. What if these are close to each other? So let's say 0.9, 0.85, let's say, and let's say 0.8. So now although the order has been maintained, but now I have brought them closer to each other. Look what happens. The allele A1 still reaches fixation, it still reaches a value of 1, but it's just that it takes a long time to go there, but it goes there nonetheless. Now of course this is happening because we are starting with a very small value of 0.001. If we start with let's say a slightly higher value, say 0.1, again the overall relationship remains the same, but the whole thing happens much faster. So this tells you that it's not merely the values that matter, values of the fitnesses, for the various genotypes. It also matters how separated they are. If all the values are close to each other, then it will take longer to reach a fixation or a high value. If they are separated away from each other, like it was in the first case, 0.9, 0.7, 0.3, then things will happen much faster. So basically it's the relative values relative to each other of the fitness which matters. Okay. So this was a situation where we saw that if you change the initial allelic frequency, the outcome is not really changing, it's just becoming faster or slower. So let's go back to our initial case, 0.9, 0.7, 0.3, 0.3, sorry, and ask ourselves what happens if we keep on changing this value of p. Am I going to get a qualitatively different thing? Is there any point for p for which instead of allele A1 it's allele A2 which gets selected, which allele A2 which gets fixed? Will that happen? And turns out that you can satisfy yourself that whatever values you put in these conditions, that's not going to happen. Okay. So now let us slightly change the things with which we are going to play. Now let's say make let's make this 0.7 and let's make this as 0.9. Let's interchange these two values and let's see what happens. The moment we do that, we find that now allele A1 is not really going to fixation, neither is allele A2 going to fixation. Instead, they are being maintained somewhere in the middle. So if you look at the actual values, it will become clear. You can see they are going to some kind of an equilibrium where both alleles are being maintained in the population, right? Both of them have frequency 0.75 and 0.25. I mean, sorry, one has a frequency of 0.75, the other has a frequency of 0.25. So, will this change if I change my initial allele frequencies? 0.3, let's make it 0.5, doesn't change. Let's make it 0.2, again doesn't change, and so on. So, you can satisfy yourself by playing with it that whatever values you put in this situation, this what is known as polymorphism, both alleles being present simultaneously, is always going to be maintained. Okay. So, starting population frequencies will not matter. So, now let us interchange these two. So, let us make this as 0.3 and let us make this as 0.9. Okay. Now, what happens? Now, you see that again one of them R, which basically means A2, that one goes to a frequency of 1 and the other one, both the genotypes go to a frequency of 0. And if you look at the simulations, you can straight away find that that is what is happening. Very soon, within 12-13 generations, this has a frequency of 1, allele A2 has a frequency of 1, allele A1 has a frequency very close to 0, which as you can see, these are extremely small numbers, they are kind of going towards 0. For all practical purposes, they are 0. So, what is it telling you? It is telling you that when you have a situation when the heterozygous is less fit than the two homozygous conditions, then again you have a situation where one allele goes to fixation, the other alleles do not. Okay. Will the starting frequency matter in this case? So, let us see. So, this is 0.2, let us make the starting frequency as let's say 8, and suddenly you have completely different situation. Now, it is P which has gone to fixation, capital P, which basically means that it is allele 1 which has gone to fixation instead of allele 2. Okay. Think about what has happened. All we have done is we have kept the genotypic frequencies the same. In one case we started with allele frequency of A1 equal to 0.8 allele A1 gets fixed, and if you start with 0.2, allele A2 gets fixed. In other words, for the same set of fitness values, which genotype gets fixed, which allele gets fixed depends on where you are starting your allele frequencies from. So, there are many other things that one can get out of this, but let us get back to our PowerPoint and let us see what are the major observations that we just now made. Our first observation was that when the survivorship are close to each other, selection is slow in changing the frequencies. When they are very different, relative to each other, then the change in frequencies is fast. Due to selection, sometimes one allele gets fixed, sometimes the other allele gets fixed, but there are situations when both alleles are present in the population, and this typically happens when you have the heterozygote to be the fittest. And in terms of the long term outcomes, sometimes the starting allele frequencies matter and sometimes they do not. Now, of course, you can keep on playing with all kinds of combinations of the genotypic frequencies and the starting allele frequencies and can keep on getting these kinds of observations. Okay. But why exactly you are getting these observations? What is happening underneath? That is something that is not very clear from these simulations, and therefore, the only way to get an understanding, a deeper understanding of what exactly is happening, under what conditions do I expect starting values to matter and under what conditions the starting allele frequencies do not really matter, etc., one has to get into the mathematics of this. One has to do an analytical treatment of what we just now saw, and that analytical treatment is what we are going to do in our next discussion. See you.